Hi there, and welcome. My name is Kathy, and I am with the Friends of Arlington's David M. Brown Planetarium. We are a nonprofit group that helps support the planetarium that is run by the Arlington Public Schools. And right now, the planetarium is indeed closed for construction, but it's supposed to open again later this year. And we hope that you'll stay tuned for information and updates on that. In the meantime, we are still doing some virtual events. We hope later in the year we'll be able to do some live in-person events, but the virtual events allow us to still do some pretty cool stuff. And today we're going to hear from Kevin Quin, who's an amazing amateur astrophotographer. He's going to talk a little bit about his work, how he does what he does, and talk a little bit about what is possible for amateur astrophotography. He's involved with the Northern Virginia Astronomy Club, and we'll talk a little bit perhaps about that. If you have questions, be sure to enter them in the chat. I am going to go ahead and turn it over to Kevin at this time. And take it away, Kevin. Thanks.
Thanks for having me. So I'm Kevin Quin, and I'm a member of the Northern Virginia Astronomy Club, which is located all throughout Northern Virginia, not just Arlington County. I have been taking images of the sky since about 2003. Okay, inside story. My first digital image of the sky was taken with my 8-year-old daughter's Barbie camera at the time by holding it up to the eyepiece of my telescope and taking a picture of the moon. Since then, I've progressed a little bit. You'll be able to take a look at some of the equipment I use as we take a little bit deeper dive and go on through the discussion. But what we're going to do is talk a little bit about how astrophotography works, and spend a little bit of time talking about gear and a little bit of time talking about techniques. But mostly what I want to do is show you the results that you can achieve and show you where that takes you through the universe. So Kathy, to flip over to the slides, am I actually on that now?
You are.
Okay. Still on it? I haven't flipped off it by mistake?
You're still there.
Okay, excellent. So I've sort of been putting this program together over the last couple of years, and then COVID. It had been designed to be done as, say, a show at a star party that the Northern Virginia Astronomy Club has. We do a couple of big public programs in the spring and in the fall, and none of those have happened for quite some time. Hopefully, this spring we can do it. But in the meantime, this is a perfect opportunity to put it online and show you what I had been planning to do. So, as I said, I call this Cosmos in a camera lens, and we're going to take a quick tour of astrophotography. And in the process of that, we're going to run through the universe at a very, very high speed. So astronomy has a bit of an image problem, which it's had for a long time. It is perceived as complicated, and some people think of it as boring. And one of the ways that you can see this is that in the library, it is sandwiched right there in the Dewey Decimal System in between statistics and surveying. So feel the excitement. But at the same time, it is simultaneously too exciting. The universe blew up and it's flying apart. And it is mind-bogglingly vast. And you can see back through time, billions of years. There are 100 billion galaxies, and each of them has 100 billion stars. And I guess that's more zeros than I have fingers and toes, although I would have to count the zeros, not the toes. Count the zeros to be sure of that. But somehow out of all of this comes the whole idea that you are utterly insignificant. You mean nothing. But maybe not, because these days you can capture it all in pictures. And in fact, we, mere mortals, not professional astronomers with access to the Hubble Space Telescope, can take those pictures. So we're going to talk about astrophotography from the point of view of amateurs. Now, back in the olden days, it was not as easy as it is now. This is a picture from Mount Palomar, the world's biggest telescope back in the middle of the 20th century. Nice for mid-20th century technology. But this is a picture of the exact same galaxy taken, I don't know, about 10 years ago with an amateur telescope over in, well, this one at the time, it was located in South Africa. While it was a nice amateur telescope and nice camera attached to it, it is certainly not Mount Palomar. It is not a 200-inch telescope, not in a professional observatory. So what changed? And probably as anybody who has tuned into this and is listening to us knows, what changed is, like everything else, computers. So this is a film picture from back in, I don't know, probably 50s, 60s, something like that. Whereas this is a digital camera picture that was not only acquired with the digital camera, but was then processed in a computer. So, quick side story. I was up at Niagara Falls a few years ago and I passed by a guy who was wearing a t-shirt that said, "I brew beer. What's your superpower?" And what jumped into my head, I mean, admittedly, this is like 10 minutes later because I'm, snappy comebacks is not what I do. I wouldn't be a geek if I did snappy comebacks. But what popped into my head was, I capture the stars. And if that's not cool, what is? So the first thing we're going to do is we'll talk a little bit about my equipment and where it's located and how I do this sort of thing. And then we'll start moving out through the universe so you can see the kind of pictures that I capture while I'm doing this. So I call my observatory the hole in the trees. You'll see why here when you look at this. This is my home, and my observatory is located behind that white picket fence. You can see that there is actually a hedge back there, and behind the hedge is where the observatory is, and you really can't see it from the street, intentionally so. That's why the hedge is there. But it's basically a shed. Now, I know that you're probably looking at this location and you're thinking, that does not look like a great location for an observatory. And you'd be right. It is probably the worst possible place to put an observatory, except for all the others. And the reason it is not the worst possible place to put an observatory is because it's in my backyard. It's literally 10 feet out my back door, and I can use it. I don't have to drive off to the back of beyond in sub-zero weather, set up all my gear, and then break it all down again, drive it all back home, and then try to do it again a week later. It's outside in my backyard, so there's no setup. It's always set up, ready to go. All I have to do is open the roof. The downside is trees, as you can see. So I can only see about 1/3 of the sky, which is why we call this the hole in the trees skybox. It is surrounded by suburbia as well, which you'll see means light pollution. We'll talk about that a little bit later. But all of my images come from here. So everything that I do comes from the observatory in my backyard, which is sandwiched in between Tyson's Corner and the new lighting enhanced Mosaic District down in Merrifield. So if any of you, I'm a stone's throw outside the Beltway. So if any of you have been there, you realize that that is not a dark location. And we'll talk about light pollution and how I deal with it a little bit later. But in the meantime, this is a picture of the observatory. You see, it's basically just a wooden shed with a metal roof, but the metal roof rolls aside. And inside are the two telescopes that I use to take pictures. One of them I use for taking pictures of the moon and planets, and the other one I use for taking pictures of stars and galaxies and nebulae. And we'll talk about how. So with that, let's go on a tour. And we'll take a few stops along the way to talk about how I take those pictures. First place we're going to visit is the local neighborhood, and as you know, as we launch on our spaceship from the Earth, the first thing we're going to run across is the moon. So the moon, as you all know, probably having seen it through telescopes and even through binoculars, is a formidable place. It's filled with craters and mountains and valleys and smooth plains and crack-like faults. The moon started out as pretty much a ball of lava, pretty much the same way the Earth did. When it solidified, it cracked. And then after that, as if that wasn't enough, it got battered by all the rocky debris left over in the inner solar system from the formation of the planets. So here's the thing, though. You see, this is a nice crater called Plato, which is up in the northern part of the moon. Very, very photogenic, right? And makes a very nice picture. But the thing is, it does not come out of the camera that way. I wish it did, but it doesn't. So let's talk a little bit about how lunar and planetary imaging works. First thing I want to show you is a picture of the planetary scope that I use in my observatory. The red object that you see there over on the right-hand end of the telescope, that is the camera. It is basically just what we would have called years ago a web camera. Today, to make it sound more fancy, they call it a machine vision camera. But it's just basically a fairly small chip, a fairly small detector in a metal box. And unlike your digital camera that may have a shutter on it, and all sorts of fairly fancy things as a lens that can be focused, this is just a metal box with a chip inside it. So the computer has to run everything else. So a computer is attached to this, runs the camera and runs the telescope that the camera is looking through. Now, that is a video camera that's on the back there. It's not really intended to be still frame. This is still pictures like a DSLR or a phone camera. It is intended to take videos, and it takes them at very, very high speeds, hundreds of frames per second. And the reason that it has to do this is that each frame that comes out of the camera in a video is dim and blurry. And as I said, when you take a picture of Plato, it doesn't look like that, because when you're looking through a camera, or when you're looking through a telescope with your eyeball, this is what you're seeing. You're seeing a boiling sky. What you can think of here is you're looking through a glass of water that is boiling on the stove. And that is our atmosphere. The atmosphere is heated up. And when you try and look through it, it is like looking through that glass of boiling water. All of the roofs, all of the heaters that are putting out heat, all of the streets that have soaked up sunlight during the day, they are all making that sky boil. And we don't want our picture to look all boiled and blurry. So each frame, though, that comes out of the camera is dim, it's blurry, because the atmosphere is boiling like that. And so we have to fix it to get our final picture. And the way we do that is we take each one of those frames from that video. And remember, the video is a collection of individual pictures. So you take each one of the frames from that video, each one of which is blurry and grainy because there's low light. Remember, it's dark, it's nighttime out there. Even through the telescope, the moon is really bright, but that's just in comparison to the other dim things in the sky. So the software that analyzes that long video, and a video might be 10 minutes long, hundreds of frames per second, so we can be talking hundreds of thousands of individual frames in that video. The software that analyzes that video will go through, it'll find the bad images, the blurriest images, and it'll toss those out. The rest of them it will keep, it will line them all up, and it will average them out to produce a single. That averaging process is what we call stacking. And it will average them out, and in the end, it will have a stacked image that's sharp and smooth, like what you're seeing on the right-hand side of the screen here. So you're still limited by seeing, though. So on the left-hand side of the screen here, at least it's my left-hand side, I'm hoping it's your left-hand side as well. On the left-hand side of the screen, you see a nice sharp image of Mars, but on the right-hand side, you see a blurry image of Mars. This was taken with the same gear, same processing techniques from the same location, just on 2 different nights. The night on the left-hand side had really good seeing. The air was steady. It wasn't boiling as badly as it might be. On the right-hand side, boiling atmosphere means bad seeing. So the computer and high-speed videos and the processing can help with bad seeing, but bad seeing is still bad seeing. You will always get better pictures on a night of good seeing. So if you go out at night and you see the stars twinkling, really pretty, but it means the atmosphere is boiling, and you're going to get images like that one on the right, not like the one on the left. So, all right, let's leave the moon behind and let's move on to some of our closer neighbors like Mars. Mars is a great subject for astrophotography. 15 years ago, no one would have said that. It would have been a lot harder, but with modern high-speed cameras, it is a lot easier to get a good picture out of Mars than it would have been. So you see here, these are 3 pictures that I took a year ago through the through the summer and fall of 2020. Mars was very close to us. Problem with Mars is it's really only close to us once every 2 years. And when it's close to us, it's this size, at least, you know, for my camera, it's this size for my telescope. But when it's far away from this, it is about the size of the South Polar Cap that you see down there at the bottom end of these pictures. So it is a real challenge to get good pictures of Mars when it's far away from us. But when it's close, like this, like it was last year, a year ago, it's easy. So these are 3 different pictures of Mars taken on different nights. Mars rotates pretty much at the same speed of the Earth. So as we go out from night to night, we slowly view different faces of Mars. And across the course of the night, if we're imaging or able to take pictures for several hours, we'll see Mars rotate. So just a couple of things to point out in these pictures. You'll see how from the left through the right, that's a process of about 2 months. And you can see how the South Polar Cap shrunk because Mars, the southern hemisphere of Mars, was moving toward Martian summer. And so that polar cap was evaporating as time went on. Other interesting thing to point out is in the view on the right, if you look at the upper part of the picture out through the desert area of Mars, that featureless orange expanse, you see a bright white spot there. That is Olympus Mons, the tallest and largest mountain in the solar system, 2.5 times the size of Everest. And the base of the volcano where that bright spot is a shield-like plateau, kind of like the Hawaiian volcanoes have shields under the water. The shield of Olympus Mons is the size of France. So it is far and away the largest mountain, let alone the largest volcano in our solar system. Now, Mars is hard, but there's hard and there's really hard. And we're going to take a step outward toward really hard, and that is Venus. Venus is not hard because of its size. It actually gets to be about twice the size of Mars, even a little bit bigger than that. The problem with Venus is that it's featureless. If you see it in visible light, like my picture on left there is with visible light. And it is always going to look like that. It goes through phases, just like our moon does, because it's between us and the sun. So we see phases on Venus. But the problem is the atmosphere of Venus is white. So there really is not a lot to see. Now, if unlike me, but like my friend Raimundo, if you have ultraviolet filters and a camera that is set up to do ultraviolet imaging, then you can penetrate down through some of those cloud layers and you can see the cloud layers that spin around Venus. And you can get some really nice imagery, which is what Raimundo is showing you right here.
So Kevin,
yeah, go right ahead.
You do have, speaking of equipment and specialty equipment, you do have a couple of questions about equipment. Do you want to hold those to the end?
No, go right ahead. This is a great time to ask questions about equipment.
You do have a question here. What equipment would you recommend for someone getting started in astrophotography?
Oh, okay. Well, so what I recommend for somebody who's starting in astrophotography is if you have a telescope now, that's the telescope that you should use. Don't go out and buy new equipment. So I will say we're going to talk about 2 different types of astrophotography here. And the type that we're talking about right now is lunar and planetary imaging. So my recommendation, if you were going to start out in astrophotography and you already have a telescope, take your phone camera, point your telescope at the moon, take your phone camera and hold your phone camera up to the eyepiece and take a still photo of the moon. Now, is that going to be, is that going to look like that image? No, it's not. But on the other hand, that's not your image, that's my image. And so you will get the joy and the satisfaction of taking a nice image of the moon with your own gear that you are then able to tweak. If you take it into Photoshop and do some tweaking on it, you can do some sharpening on it, you can change the brightness of it a little bit. You can do that yourself. So without any gear, you can do that. If you don't have a telescope, go out to a meeting, go out to an observing session that the Northern Virginia Astronomy Club has, and go to somebody's telescope and hold your camera up to the eyepiece of their telescope. And you can get a wonderful picture that way. So that's the way I would start out. But if you're going to take a little bit deeper dive, I would save that for when we're talking about deep sky imaging, taking pictures of the stars. There are different approaches to doing this. And like I say, if you've already got a telescope, you can actually get an iPhone holder, or well, a camera phone holder that will allow you, it's basically a bracket that you attach to the back end of your telescope. And you can, instead of having what I have, which screws on to the eyepiece end of my telescope, that red camera just screws on, it's threaded. But you can instead get an iPhone or a camera phone holder that's just a bracket that clips onto the eyepiece end of your telescope, and it will position the lens of your phone camera in the right place so that you can take pictures through it. So, that is the way that I would start in imaging. If you have a very small telescope, don't try and do this. This is hard. What I do, use a small telescope, particularly a telescope that you have, and get one of those iPhone holders. You can buy those online. They're, anywhere from $25 to $100, which I assume maybe at least roughly correlated to quality, which translates to how steady they can be held on the telescope. But that's how I would start out. For deep sky imaging, it's a little bit more complicated. I'll talk about that, imaging pictures of the stars and galaxies and nebulae. I'll talk about that when we get to that section. But that's what I would recommend.
That's great. And before you move on, Kevin, related to that and partially what you've been talking about here, this sort of fits in. What are some good targets if you are getting started, perhaps with that small telescope in the iPhone or the camera phone that you were talking about?
Always the moon. That is far and away the easiest target to take pictures of, and the target that you will get the best pictures of, the best results of. So I would always say start with the moon. Now, the techniques that we apply to take pictures of the moon and planets and the techniques that we apply to take pictures of deep sky objects are different. You'll see that there are some similarities too, though. But deep sky objects are challenging because they are really, really faint, and you need to have long exposures. And to take long exposures, you're talking about an entire different level of gear. Everything has to be held very, very steady and for extended periods of time. Whereas taking pictures of the moon and the planets, that is a lot easier because you're taking videos, like particularly as we're talking about for the moon, those videos can be 100 frames per second, even more than 100 frames per second. And so each particular image is very, very short, and the moon is very, very bright. So you don't have to hold the camera steady, at least not anywhere near as steady as you do for deep sky objects. That's why I'd always recommend start with the moon. Once you feel like, oh, okay, I've kind of got a handle on this, I know how this works, then you can think about going to stars or deep sky objects. And I will talk a little bit more about how you do that. Anything else on that?
No, that's it for now. Thanks.
Okay, great. All right, so let's go back to the planets here. So Venus, we're getting harder, much harder than Mars. Let's make it a quantum leap inward toward Mercury. Mercury is a little bit bigger than our moon, but it's not a lot bigger than our moon. But otherwise, it is, cratered mountains, much like our moon is, no atmosphere. And so if you saw it up close, it would look very much like our moon. The thing is, it is tens of millions of miles away, whereas our moon is only 250,000 miles away. Also, Mercury is really close to the sun, meaning that the practical result of that for us is that it never gets very far above the horizon for us when we're looking at it. You see it in the morning for a little while before the sun comes up, and in the evening for a little while before the sun goes down, but you're looking at it through our boiling atmosphere. Now, if Mercury was straight overhead, well, that's where the atmosphere is thinnest, right? Because you're looking straight up. But Mercury is going to be close to the horizon. So you're looking through a lot more air. And because the sun is getting ready to come up or the sun has just gone down, that air tends to be a lot less steady than it would if you were imaging in the middle of the night. You can't. It's Mercury. You got to image it before sunrise or before sunset. So it's hard. The images that you're seeing here, these are some of the best images I have ever seen of Mercury. At the top is a computer simulation, and you can see how the actual telescope images down at the bottom match up to that computer simulation. These are really good. But as you can see, Mercury is a very challenging target. The thrill that people get out of taking pictures of Mercury is we have sent very few satellite missions to Mercury. So taking pictures of Mercury, you're still getting things that there is not a satellite in orbit around Mercury at all times to get these images. So your image may be the only one that is being captured at that particular time. All right, so let's go outward now. We're going to go back to making it a little bit easier again. These are my pictures, and first stop is Jupiter as we go outward from the solar system, outward from Earth instead of inward. Jupiter is a great photogenic target. It is huge. It gets up more than twice the size of Mars, so it is much easier to take pictures of. It's around pretty much every 13 months, so you can get access to it a lot more often than Mars. And it is fairly photogenic. The contrast is, as planets go, the contrast is fairly high. And the other cool thing about Jupiter is things change on Jupiter. So not only does Jupiter have moons that go around the planet and occasionally pass in front of it and cast shadows on the planet, but the moons themselves, if you have enough magnification and enough resolving power with your imaging system, the combination of your telescope and your camera, you can actually see detail on those moons. So in the center image here from 2014, you can see the moon Ganymede on the left there, and on the right is Io. Ganymede is a moon a lot like our moon. There's no real atmosphere, but it is very, very large. I think it's about half again the size of our moon, but otherwise is, from a distance at least, looks like our moon. It's not really covered with rock. Most of it is ice on the surface. Io, on the other hand, the reason that Io is that orange color is that it's covered with sulfur. And the sulfur is from sulfur volcanoes. Io is very close to Jupiter, and it flexes from tidal forces as it goes around Jupiter, heats up the interior of Io, and for whatever reason, a lot of Io is sulfur on the inside. Sulfur melts, spews out through volcanoes, and coats the surface of Io. So that is why you have that lovely yellowish orange color for Io. A couple other nice moons, Europa and Callisto, that I don't have in this picture, but they also are photogenic targets. The one other thing that I'd point out about Jupiter, other than the belts moving, the clouds changing, in a half hour, you would notice that not only had Jupiter rotated, but if you looked really, really sharp, you would see that the individual clouds start to move on Jupiter. But one of the cool things that happened back in 2010 was the southernmost of the two big belts on Jupiter disappeared altogether. So you see the red spot there, and there should be a dark belt wrapped around the red spot, and it's not there. It is in 2014 and in 2016, and it is there now, just every once in a while, it disappears. I think we understand the science. There is a new type of particle that gets spewed over the top of that dark cloud belt. The dark cloud belt is still there. It's underneath white particles. But what causes that to happen on a periodic basis, I have not heard good science on that. Let's make it a little harder. We'll move outward towards Saturn. Saturn is much smaller than Jupiter and is, because it moves more slowly around the sun, it is less available to us than Jupiter. The fun thing about Saturn is the rings change orientation. Depending on the geometry between us, Saturn, and the sun, we may see Saturn with the rings edge on, like in the left-hand picture there, or we may see it with the rings fully open, the way it is in the center picture. In 2021, it is partly closed, the way it is on the right-hand picture there. And you can also see the progression in imaging skill as more and more advanced hardware and processing techniques have come available to us amateurs. You see the progression in quality between the image on the left and the image on the right. So things do improve for us over time. So we're going to take a brief pause for science here. You all may have noticed the change between the rocky planets, Mars and Mercury in particular, but Earth, to some extent Venus, which is shrouded under clouds, but is a rocky planet, and these gas giant planets as we've moved into the outer solar system. So why? What caused that? Well, when the sun lit up, when the nuclear furnaces of the sun lit off early in the history of the solar system, the winds and the heat that the sun put out blew out the remaining light gas from the inner solar system. That's mostly hydrogen and helium. It blew that gas into the outer solar system, where it was swept up by Jupiter and Saturn in their growing phases. And so most of the material in the solar system that is not in the sun is in Jupiter and Saturn. The rest of us are the dregs. And as you get out past Saturn, there was still gas out there, but Jupiter and Saturn had first dibs on all that gas. So the ice giant planets, Neptune and Uranus, got the dregs. Some hydrogen, some helium, some heavier gases, but a lot of water ice out in the ice giant planets as well. But these are also further from the sun, and a lot of the materials that we might find as gases on Jupiter and Saturn start to freeze out as you get out to Uranus and Neptune, the real reason that they're called the ice giants. The thing about these guys is they are really, really far away from the Earth, and they are really, really tiny. So just like taking pictures of Mars when it is very, very far away from us, these things are tiny little, they're not specks through the computer, through the telescope, but they are dots. Let's call them like the dot on the end of a sentence. And so mostly Uranus is a nice greenish blue dot, and Neptune is a nice bluish green dot, but dot is the operative phrase there. If you work really, really hard and you have the right gear, you can actually see some details on both of these planets. The picture in the center there is Uranus taken through infrared filters, and you can just make out the one dark belt that goes around the equator of Uranus. If you got really lucky and had a very nice night in the right gear, you might see some white clouds on Neptune. But really, really difficult stuff. Mostly what we image when we image Uranus and Neptune are the moons. Uranus has 5 of them that we can capture. In the image on the left there, you see that there's 4 of them. Neptune only has 1 moon that we can really capture in our cameras, and that's Triton, that you see to the left of Neptune in the picture that we've got here. So Before we leave the solar system, I know that there's one question that maybe some of you have thought of when we're talking about the history and why the gas giants and the ice giants are in the outer solar system. As we have discovered planets around other stars, you may have heard of this thing called hot Jupiters. And that is what happens when you get a planet like Jupiter up next to the sun. And it's still there. Somehow that happened. And the reason is that planets don't necessarily stay where they are formed in their solar systems. For various reasons, interactions between the planets or perhaps a nearby star passed through and it disrupted the gravitational balance of that solar system. And some of those planets can migrate inward from where they formed and accumulated all their mass and migrate much closer in toward their sun. That's how you get that phenomenon of hot Jupiters. Now, for various reasons, all of them good, our solar system did not go through that experience. So our Earth pretty much stayed where it formed. Jupiter stayed out where it can be a well-behaved Jupiter and not disrupt the rest of the solar system. And as a result, we humans exist on Earth because there's life here. So one more stop before we leave the solar system, which is comets. As you go past Uranus and Neptune and even Pluto, you come to the realm of the comets, the Oort cloud. Where comets spend most of their time. Every once in a while, one of them takes a nice dive through the inner solar system, like Comet Leonard, which passed by the inner solar system over the last couple of months. And amateurs can get nice pictures of a beautiful comet like this. Now, this is a comet that is beautiful to astrophotography, but with your naked eye, Comet Leonard was small and faint and distant. Both with astrophotography and the right techniques, it itself reveals all of its structure. That's the end of the solar system. Before we leave the solar system, I'm going to take a quick pause before we dive into the deep sky. You'll see that we start some different techniques here, and we'll talk about those a little bit later. But as we head out of the solar system, the first star we come into is Alpha Centauri, which is about 4 light years away. If you want to think about it, if our sun was the size of a basketball, the nearest star would be in Cincinnati. So it would be a long trip from our sun to Alpha Centauri. We're going to go a little bit further than that to the first star. We're going to stop at Sirius, which is the brightest star in our sky. It's not actually not the brightest star in the galaxy. It just happens to be, in addition to being a reasonably bright star, it is only 8 light years away from us. And this is in a galaxy that spans 100,000 light years. So it's bright, but it's not super bright. It just happens to be very close to us and is much brighter than the other stars that surround us. Sirius, in fact, is 2 stars. Our star is single, which is probably a good thing. Remember, life exists on Earth, and that may very well be one of the reasons. But most stars in our galaxy like company, and Sirius is one of them. There is a very, very faint white dwarf in orbit around the big bright star that we think of as Sirius. Can't see it in this image, but in fact, most stars in the sky have companions. This is Alberio, one of the beautiful color contrasting double stars in the summer sky. And like I said, most of the stars in our galaxy, and presumably most of the stars in the universe, are double stars, triple stars, even more complex systems than that. So stars are gregarious, and most of them formed in clusters, like this one. This is called the Owl Cluster. It's a nice cluster in the autumn sky. Oop, wrong direction. This is M103, another nice cluster in the autumn sky. Stars tend to form in those clusters, but there are different types of clusters. This is a globular cluster, and you'll see there's a nice contrast between that globular cluster and this one. This is the Great Globular Cluster in Hercules, M13. One of the nicest from the northern sky where we are. There's some very nice ones in the southern hemisphere that we don't have an opportunity to see. But you can see there's an obvious difference between these open clusters and the globular clusters like M3, which is this one, and M13. So what explains that? Well, star clusters, we think, are born in the same way. They clump together out of gas in our galaxy, but they evolve in different ways. Some star clusters may get tossed outside of our galaxy to go into a distant orbit around our galaxy. Other star clusters stay in our galaxy and for whatever reason don't get ejected from the galaxy. The ones that stay in our galaxy, those are the open clusters like these ones. And the thinking is that as the galaxy rotates and as pressure waves and other things happen to these star clusters through the history of our galaxies, they slowly start to break up and drift apart. On the other hand, globular clusters like these that got tossed out of our galaxy in their youth and only pass through the center of our galaxy every once in a while on their orbits, they tend not to get broken up. They're not subjected to those same galactic forces that the open clusters are. So these globular clusters like M3 and M13, they can be billions and billions of years old. They're some of the oldest things in the universe. Whereas those open clusters, they tend to be tens of millions of years old. They break up over time. All right, so you all may have noticed that we have changed subjects here. We have gone from lunar and planetary imaging in our solar system to the deep sky. And now we are taking pictures of star clusters. And in a minute, we're going to be showing you pictures of even more challenging objects like gas clouds and galaxies. So this is a new type of imaging, deep sky imaging, and it is subjected to a new plague. That plague is not seeing. It is subjected to seeing, but seeing is not nearly as much of a challenge for deep sky imaging like this as it is for planetary imaging. The real plague that we face for deep sky imaging is light pollution. So welcome to Tyson's Corner. I mean, not really, but maybe in a few years it will get this bad. And as I told you, my observatory is sandwiched in between Tyson's Corner and the Mosaic District. So light pollution is something that I am very familiar with. It doesn't get dark from where I am, like as if you were going out to West Virginia. So if you look at this image that's on the right-hand side here, this is cribbed from an astrophotography book. The stars are what I want to take a picture of, right? And the stars are sending their light down to land on my camera sensor. But the other thing that's sending its light to land on my camera sensor is light pollution. That's what the sky glow signal is. And so I got to get around that because otherwise I'm just going to have, well, a picture like this, Tyson's Corner, right? So how do I do that? We'll take a quick stop. This is my deep sky imaging scope. You saw I had 2 telescopes in my observatory when the roof was open. This is the deep sky telescope, much more complicated than the planetary imaging scope, has to deal with a lot more things, but not a totally different phenomenon. In fact, the telescope itself is the same. I use the same telescope, the same type of telescope for deep sky and planetary imaging. It's got an 11-inch mirror, and it casts its light back onto a camera way back the back end of the telescope. But I use some special filters in that big black disc that you see at the south end of the telescope there, in between, right above the camera, that sort of black cylinder at the far end of the telescope, that's the camera. But that black disc you see in front of it, there are special filters inside there. We will talk about them. But the real trick for how I get around light pollution isn't those filters, it is time. Now remember, I got an observatory in my backyard. So even if the sky is only going to be clear for an hour, I can go out there, open it up, take pictures for an hour, and then close it up before the rain comes, before the clouds come through. So I can get hours and hours, sometimes even days of imaging time on a single object. So how do I do that? So time is the real key. And unfortunately, time is not all by itself the solution. When a picture comes out of the camera, it doesn't look like that finished picture that you saw. It's black, like that picture on the left. If we give it enough work and we stretch it, we can make it look like that picture on the right. So that's something you do in Photoshop. You go from your nice dim image to your more brightly lit image. And it is a process of using a tool called curves or adjusting the histogram. And we can make it look like that brighter image on the right. But as you remember, the pictures that I show you don't look anything like that, because that's not a finished image. If we zoom in, the image looks like that. So you can see we're looking at stars here, and this is a very, very close-up picture of the stars. And you can see the stars here, but in between the stars, you see all that graininess? That's noise. So all those empty spaces in between the stars should be black, right? Because we're looking into empty space. But because of light, well, okay, because of light pollution, I guess they should be gray, right? But it should be a nice, even, uniform shade of gray. But it's not. Do you see all the individual pixels there? Some of them are lighter, some of them are darker. And they're not supposed to be that way. But you see that's random variation. Now, if you think about pictures that are taken in very low light from your phone camera or from a digital camera, that's what we're doing here. We're taking pictures in very low light, and they look grainy, right? And that's exactly what you're seeing here. This graininess that you see in low light photos from your own camera, that's what you're seeing here. We call it noise, but it's the same thing. It's the same phenomenon. Now, the other thing is, in addition to being random noise across where that black sky or gray sky should be, you see there's noise that varies in between one picture and the next. So these pictures were taken one after the other. And you see the stars are in the same place. You see those pixels, the noise varies. So that's because the universe is random. You've heard of quantum mechanics, because I know you are astronomy people. I'm going to give you a really short explanation of what's actually going on in the camera. We're going to go full geek just for a minute here. So photons come from the stars, from the galaxies. They hit an individual pixel in your camera. And my camera isn't that different from your camera. There's a detector in all of these cameras, and they have pixels. So the photons strike a pixel, and when they do, it releases an electron. And the electrons build up during the course of the exposure, and they fill what's called that well, where all those little green balls, which are electrons, are building up on the left-hand side image here. So the well eventually gets read out. The chip, the entire detector, gets read out by the computer, and the computer looks and it sees, okay, well, there are 2,158 electrons in that well. So we're going to turn that into an image value of 2,158. So let's say, 10,000 would be fully white and 0 would be fully black. And it just so happens that this pixel of the nice gray, smooth sky background has a value of 2,158. Now remember, every pixel should have that value, because we're looking at a nice, smooth gray sky. There's no star there. So the pixel next to it should be 2,158 too. But if you look at the pictures, the pixels that are set up in that array here, above the 4 in this image, you see that they're not. The one above is 2,111. There's one that's 2,108, one that's 2,198, one that's 2,240. Quantum mechanics. The pixels are not all the same, because one patch of sky and the next patch of sky don't necessarily spit out the same number of photons at the same time. And between one exposure and another, even the same patch of sky doesn't necessarily spit out the same number of photons. So in the end, I have these nice grainy pictures, and I have a whole assemblage of these nice grainy pictures. Because remember, I can't expose forever, because eventually that well fills up. And if I put more electrons in that well than it can hold, it's white. The entire picture is white. It's just like back in the film days when we'd have an overexposed picture, when everything would be white. So I've got to take a whole series of pictures like this, and they'll be nice and grainy like this. So what do? You remember our friend stacking from planetary imaging? We do the same thing with deep sky imaging. We take all of those noisy images and we stack them up with the computer. And in the end, the noise averages out, and it's nice and smooth, because noise is random. And so when you average out all these noisy background images, you get a nice smooth background, but your target is still there. So now we can separate out the star cluster. We can separate out the galaxy from the noise in the background. That is how stacking works. And it is the secret both for lunar and planetary imaging and for deep sky imaging. Now here, the computer isn't going through a million images. There's probably only tens of images, maybe hundreds of images, because instead of taking 100 frames a second, I'm taking one frame every 2 minutes, or maybe even every 20 minutes. So I can go through with my eyeball and I can toss out the blurry ones. Then the computer stacks them all up, and that random variation, that noise averages out, and the background gets smooth, and the stars are visible, and you get this. Now this is 362 2-minute exposures, but it's the same target. Let's go back to a single exposure. There's a single exposure, another single exposure, and here's 362 exposures. So you can see not only is the noise greatly reduced, that background becomes very smooth, but you can see there are stars here that you couldn't even see in these images. I can see maybe, I don't know, 8, 9, 10 stars there. But here I can see dozens of stars in this image. So that is the magic of astrophotography. That is how we do it, stacking. It makes blurry objects sharp and it makes dim objects visible. So I can take short images for hours and hours and hours, and I can image across multiple nights, and I can get that noise level way, way down to show really faint stars and really faint galaxies. But some things are very, very dim. Now, the universe isn't all stars. It's mostly made of hydrogen. And there's a little helium out there. And there's a trace of heavier elements like sulfur, oxygen, and nitrogen. But there are vast clouds of this stuff out there, and they are highly photogenic as well. So the Horsehead Nebula, that probably some of you are familiar with in Orion in our winter sky, there are clouds and clouds of this stuff that fill our galaxy. And so there's plenty of stuff out there to see and plenty of photogenic things to photograph. So what happens is when those clouds are heated up by nearby stars, they glow in very precise colors. So if you remember chemistry class from high school or college, hopefully you took it, I didn't, but I've learned it since then. When hydrogen is heated up, it emits light at very specific colors, and only those colors. When oxygen is heated up, it emits light at a very specific wavelength, and only those wavelengths. Now, there are really only 3 gases out there that I'm interested in. There are 2 shades of red. One of them is for hydrogen, and that also pulls in nitrogen, because the nitrogen and hydrogen colors are very similar. They're almost exactly the same shade of red. There is one slightly deeper red for sulfur, and then there is a third color, teal green, for oxygen. Those are the 3 colors that the vast majority of the universe emits, right? But what about light pollution? Well, light pollution is all colors. Remember our picture of Tyson's Corner here? And that's everything, right? Light pollution is white. But the targets that I'm interested in, they're not putting out white light. I mean, to some extent they are, but the gas clouds are mostly emitting in 2 different shades of red and in teal green. And if I can use filters that cut out everything except those particular colors, then I can cut out almost all of the light pollution in the sky, and I can get only the things that I'm interested in taking pictures of. So that is the second trick of astrophotography. Narrowband filters, that's what this is called. And almost all of us use these 3 filters, one for oxygen, one for hydrogen and nitrogen, and one for sulfur. And that gets us pictures of pretty much everything that we've got. I can cut out the great majority of light pollution. I mean, there's still light pollution in those 3 colors, but most of the light pollution is other colors. So now I've made the ratio of good light to bad light that falls on my camera detector much more favorable to me. So what are those gas clouds from? They are from dying stars. This is a planetary nebula. This is the Ring Nebula that probably some of you have heard of before. These dying stars, when they get to the end of their life, stars like our sun throw off most of their gas. This is M57, and M57 has a nice little ring around it. That's why it's called the Ring Nebula. M27, the Dumbbell Nebula, HDW2. You can see planetary nebulae come in all sorts of colors and sizes and shapes. They're sort of like the flowers in outer space. Bigger stars that are much, much bigger than our sun, they die in a different way. First of all, they only live about 10 million years, unlike maybe 10 billion or more for our sun. They live fast and die young. And they throw off, sorry, this is another planetary nebula. This is the Helix Nebula down in our autumn sky. But big stars will throw off most of their gas in their first few million years, and they blow up bubbles like this. This is the Bubble Nebula in the autumn sky up in Perseus, well, up in Cassiopeia. This is another bubble, again thrown off by a really bright star. And those stars, over the course of a few million years, will throw off most of their mass until, boom, supernova. This is the Crab Nebula that probably many of you have heard of. It exploded about 1,000 years ago and was recorded by Chinese astronomers. But there are plenty of other supernova remnants in the sky. This is a big close-up on the Veil Nebula. And this is the entire Veil Nebula seen from a distance. So maybe 10,000 years ago, at the center of that area, a star went supernova and blew up. And 10,000 years later, that gas expanding out from the explosion is what we see. So then the cycle starts over again. That gas eventually condenses down into new gas clouds. This is the Orion Nebula, and forms a nursery where that gas condenses down into new stars, and they light up the same way our sun did way back at the origin of the solar system. This is M16, the Eagle Nebula in our summer sky. Now, it is this process is why the universe, which is now 14 billion years old, is not filled with nothing but black holes. This is why there is stuff in the universe, because stars get recycled. Even supernovas blow off most of their gas in their death throes, rather than taking it to the grave, to the black hole phase with them. So this is why there is stuff in the universe, as opposed to just a whole garden filled with black holes and nothing else. And it, of course, is why we're here too. All right, so now we're going to move out, and we're going to move very fast. We're going to take a very quick tour into the very, very deep sky. So what about galaxies like the Andromeda Galaxy, Messier 31? Well, they're white because they're galaxies. They have stars, and stars are all different colors. So light pollution filters, narrowband filters, they won't help me. Only time. And I need to take dozens and dozens of hours to take some of these pictures. M33, another one, member of our local group. These two galaxies are only about 2 million, 3 million light years away. But now we're going to move quick. We're going to move away from our local group of galaxies, out into our local cluster of galaxies, which is called the Virgo cluster. This is M64, the Black Eye Galaxy, 17 million light years away. NGC 3521, which is 26 million light years away. M104, the Sombrero Galaxy, which is 30 million light years away. Nearby, but in the other direction, is M51, the Whirlpool Galaxy, 31 million light years away. And then moving further out, M109, 83 million light years away. Now, you know, we've been talking about the Virgo cluster, and you see other galaxies gathered around M109 here. Galaxies, just like stars, they like to cluster. And clusters of galaxies like to cluster as well. They form superclusters. So right now we're heading out into the edge of our own local supercluster, which is called, we've left the Virgo cluster, which is our galaxy cluster, and we're moving through the Laniakea supercluster, of which our Virgo galaxy cluster is one member. But now we're going to leave that behind. We're going to take a deep dive, 300 million light years through the Taurus void to the universe's next thing. Whoop, wrong direction. We're going to reverse. We're going to go across the Taurus void, 300 million light years of basically nothingness, to the universe's next thing, the galaxy clusters that form the Perseus Pisces supercluster, which stretches about across about 1/4 of our night sky. We're going to start with the Perseus galaxy cluster, Abell 426, which is one of the largest galaxy clusters known. It anchors the north end of the Perseus Pisces supercluster, and that supercluster includes Abell 262, The NGC 80 group, both of those are in Andromeda as we're heading south from the north end of the Perseus Pisces supercluster. And we wind up the south end, the Pisces cloud. Now, these galaxies are 350 million or so light years away from us. I can still record them in my telescope because even 350 million light years isn't too far. But as we leave the Perseus Pisces supercluster and we go even deeper, we'll come to the Hercules cluster, which is merely a small piece of an object that you may have heard of called the Great Wall of Galaxy Clusters. It is one of the largest known structures in the galaxy. It is a long, long sheet of galaxy superclusters, an object that was thought not to even be possible until, say, 20 years ago, 30 years ago. This part of the Great Wall, the Hercules cluster, is 500 million light years away. As we move even deeper through another void, we come to the Corona Borealis cluster, which is 1 billion light years away. And now you can see those galaxies are getting very, very small and very, very faint. They're also getting very, very yellow because redshift. The farther things are away from us, the farther they're moving away from us. And the light from them starts to get shifted toward the red end of the spectrum. So instead of seeing nice blue spiral galaxies here, I'm now seeing nice yellow spiral galaxies or even red spiral galaxies. So we're 1 billion light years away now, but we're still not at the complete end. We'll go a tiny bit further away. Now these 5 galaxies that you see in the foreground are Hickson 58. They're only about 500 million light years away. But if you look to the left, to the upper left, you see a clump of galaxies. That's Abell 462. I'm sorry, 1454. That is 1 billion light years away, or 1.5 billion light years away. And if you look to the right, you see another clump of galaxies. That's Abell 1456. That's 2 billion light years away. Beyond that, you're moving into, you've redshifted so far that the light that you're trying to capture is no longer visible to your detector, at least not to mine. This is what the James Webb Space Telescope will do. It is designed to get infrared light, especially deep infrared light that is beyond the reach of ground-based telescopes. And so if you want to get much beyond the 2 billion, 3 billion light year limit of what my telescope can do, then you're talking about James Webb, except for one thing, and that is quasars. Quasars are the brightest objects known in the universe. We think that maybe there are very, very early galaxies. Because they are so bright and emit so much ultraviolet light, that ultraviolet light is also redshifted, but it's redshifted down to become visible light that my camera can record. Now, these things are not particularly photogenic. Some of the red dots that you see in the background here, they are quasars. But this particular image contains a quasar that is 12.5 billion light years away. It is far and away the most distant thing that I have ever taken a picture of, and it was formed when the universe was only 2 billion years old. So now that's a kind of esoteric and very geeky thing that I look at a tiny little red dot in my picture and I think, wow, that is really cool. But that is kind of the way it is. I guess I would say as we come to the edge of our universe here, and to the end of our tour, we've come a very long way. And you may ask, well, why? Especially if we're talking about tiny little red dots. And I guess I would say that there really is no why. You all who are friends of the Planetarium are interested in astronomy. So I think I probably wouldn't surprise you when I say I explain it to my family as, well, some guys play golf and I explore the wonders of the universe. And I win. Just kidding, mostly. But that is the way I think of it. But I want to emphasize that, as you all know, being friends of the Planetarium, you really don't need all the fancy gear to appreciate the universe. All you really need is a sense of wonder. Because when you go out and you stand up and you see the moon in the sky, I feel it every time. And so as we end, let me say that I hope the next time we meet, we are standing under a dark sky, without clouds, looking up. And with that, I am happy to answer any other questions that I didn't get to.
Okay, Kevin, we did actually have another question in here, which was, is the software for processing the lunar and planetary images the same as the processing for deep space photos?
Excellent question. And no, it is not. The difference is that the software that processes lunar and planetary images, because it's looking through hundreds of thousands or even millions of individual frames, it has to be able to sort out the blurry ones, right? So there are tools that it uses when it looks at each of those individual frames and it tosses out the bad ones. And it has to be high-speed software that can do that. So it's maybe taking some shortcuts that we don't have to take with deep sky images, because the deep sky images, there's only maybe a few hundred of those. And like I said, I'm going through with my own eye and tossing out the bad ones. So the computer doesn't even have to do that. The computer does do some evaluation, even on the deep sky images, and decides which ones are sharpest and which ones have the most contrast in them. And it gives those a little bit higher weight when it does the averaging calculation. But it is a different type of software. The other thing I'll say is the software that I use to stack lunar and planetary images is free, whereas the software that I use to stack deep sky images is definitely not free. There is freeware for that, but the software that I use is in fact not free. But they're doing two very different types of image analysis. The stacking process itself is very similar, but there are different burdens on those two different pieces of software, so they're running different things.
So, I want to emphasize the images you were showing us were images that you personally and other amateur astrophotographers took. These were not Hubble images. These were not things done by super duper, NASA scopes. They were things that you yourself and others like you have created, correct?
Yeah, exactly right. Like the image you're seeing behind me, it was taken from that observatory in my backyard. And all of the images that you've seen here, other than that first one from Mount Palomar in the 1950s, all of the images that you've seen here were taken from amateur telescopes. Most of them were mine. There were a few from other members of my club, a couple from friends overseas.
But it's not simple, as you've been saying.
Yeah.
How much for some of those deep sky images, how many hours of imaging and how many hours of post-imaging processing do you think it takes for you to come up with a finished image that you're happy with?
So for capturing the images, for like the image, like the one that you're seeing behind me, that was probably about 18 hours, right? That's a narrowband image. So those three different filters that I was talking about, the oxygen, hydrogen, and sulfur filters, I try and collect 6 hours of data through each one of those filters. So 18 hours total. And it probably took me that long to process it. Now, I will say that is because I agonize over my pictures. If I got to the end of processing it and I looked and I said, I like that is the way I want to process it, to actually repeat that would probably take me about 20 minutes, right? But it is the process of like stretching, the first step that we talked to when you go from a black picture to a picture where you can actually see your objects. It is that process that I spend a lot of time thinking about, because you want to stretch it as much as you can to get all the details out of the background. But if you stretch it too much, it starts to look like garbage, because you get all that graininess starts to, you can't suppress it forever, right? So I spend a lot of time agonizing over, well, how much do I want to stretch this image? How much do I want to stretch that image? But the actual process from there, is reasonably mechanical. It is that process of deciding what tweaks I want to make, as opposed to the actual making the tweaks. If somebody said to me, okay, here are the settings that you want to use for this particular image, like I say, I could probably do it in 20, 30 minutes. It's the art aspect of it that takes the time to figure out, well, what do I want the picture to really look like? That's what takes the time.
So speaking of the art, could you talk a little bit about the color of the images?
Oh yeah, that's a very good point. So for deep sky images, like I said, for planetary images, I'm using a color camera. So I don't really need to do much to make Mars look the right color. The moon, doesn't really have any color in it to begin with, right? So, I adjust those colors a little bit, but it's pretty straight. That really pretty much is a mechanical process, right? Now, for the image the deep sky images, like the one you're seeing behind me, remember I collected this data with three different filters, but it's a monochrome camera. It's a black and white camera, right? So what I do is I've got a set of images taken through the oxygen filter, a set of images taken through the hydrogen filter, and a set of images taken through the sulfur filter, but they're all black and white. I have to tell the computer, oh, those oxygen images, I would like you to use those for blue. The sulfur images, I would like you to use those for red. And the hydrogen images, I would like you to use those for green. And then when the computer puts it together, it gets this color image that you see behind me. That's how I go from a black and white camera to color images. Because when you tell the computer, okay, blue is that filter, red is that filter, green is that filter, then it knows when the computer is highlighting a green pixel, it uses the hydrogen data. When it's highlighting the blue pixels on your computer, it uses the oxygen data, etc. That's how I get a color picture out of a black and white camera.
Great. Do you have any other advice for folks? What about, isn't there an imaging group that you're involved with
Oh
Novak?
yeah. So the Northern Virginia Astronomy Club has an imaging group. We get together about once every couple of months, compare our pictures. We usually have a presentation where one of the presenters will talk about how those pictures are put together, or how the pictures that person did were put together. And it takes a fairly deep dive into the techniques that were used for putting that together. If you go to the Northern Virginia Astronomy Club website, there should be a link there that tells you how to get to our the imaging group meetings. They're online, just like this is now, and we're happy to have anybody drop by who would like to. Strongly encourage you to participate in the astronomy club itself. Pictures are nice, but I can tell you that, especially for the moon, there is nothing like seeing the moon through a telescope with your eye, or even through binoculars with your eye. I can make pretty pictures, and they're nice and sharp, and they're nice and detailed, but I don't know, that silvery glow of the moon is just something that you just can't capture except with your eye looking through a telescope. So I strongly recommend that you go to Novak's website and go to one of the many star parties they have that you can just drop in and look through dozens of different telescopes and really get a sense of how this all works.
Great. If anybody has any additional questions, they should go ahead and post them in the chat now. We'll give everybody just a moment here to see if there are any additional questions. We've had some good ones so far.
I want to answer the one question that we had raised earlier when we talked about how to get started in this. And I had said, for taking pictures of the moon in particular, just find somebody with a telescope and hold your phone up to the eyepiece and take a picture. Or if you want to take a little bit deeper dive, get one of those brackets for your phone. You can do the same thing for deep sky imaging, but it is more challenging to get good results from deep sky images than particularly from the moon. because like I said, you need long exposures to really get good data. Whereas for the moon, a snapshot can actually be quite nice, because a snapshot is very, very short, and you don't really have to worry as much about that boiling atmosphere if you take a really quick exposure. Like if I showed you a single exposure of the hundreds of thousands that I took, one single exposure, it wouldn't be too bad, right? And one single exposure from your phone camera won't be too bad. But for deep sky images, time, and lots of it, is the answer. And that is definitely a harder thing to do. And if you're thinking about doing that, definitely go out to one of Novak's observing sessions and go around and find the people who are taking pictures through their telescopes. Ask them what they do. There is a crazy hard way to jump into deep sky imaging, which I will confess is what I did. But I can tell you the learning curve for that is almost vertical. And there's an easy way, which is basically putting your DSLR on top of a telescope that already is looking at the stars. That's the easy way. Don't worry about the telescope. Don't worry about the mount that it's on. Either find somebody who has one or borrow one from Novak. We loan out telescopes. Borrow one and just put your camera on top of it and take pictures of the stars and see what you get. That is the way I would always recommend somebody start out in deep sky imaging.
And how many years have you been doing this?
I took my first digital image with the Barbie camera back in 2003. But I was really only had started doing planetary imaging, say from 2003 to 2008 or so. But then, which is easier, like I said, it is easier. But then I went to one of Novak's star parties up in West Virginia, and I won at a raffle a deep sky imaging camera, which I have described since then as the most expensive free thing I have ever owned, because it got me into deep sky imaging, which, like I've said, is an entirely different kettle of fish, and an entirely more expensive kettle of fish, particularly if you take it to high magnification. Everything gets harder. As you magnify the size of the things that you're taking pictures of, you are magnifying the difficulty of taking those pictures as well. And because a picture is a two-dimensional object, it increases the square of the size of the picture that you are taking, not just linearly. So it is certainly more challenging and more expensive to take images of individual galaxies, individual star clusters, and particularly very, very faint objects. So, but that is how I got into that. And so I've been deep sky imaging since about 2008. And I did do some film imaging back in the 80s through the early 90s. But that was back in the days when I did take my own advice. And I just got a regular film camera, attached it to the top of my telescope, and opened the shutter and took pictures. And again, that's why I'd recommend that anybody get started with a digital camera today. Attach it to the top of a telescope that's already tracking the stars, and open the shutter and take pictures. See what you get.
So last question, do you have a favorite object to
Ooh, well, the moon, really. I mean, for lunar and planetary imaging, there's nothing like the moon. It's easy, the contrast is high, and it's huge. I mean, obviously, it's not as big as a planet because it's so close to us. There's so much detail on the moon that you can get lost on it. You can image the moon forever, and you'll and it the phases change, so you will never be finished imaging the moon. For deep sky objects, I have always really been interested in galaxies. And the problem is galaxies are far and away the hardest thing to image from where I am. Because, like I said, narrowband filters help for gas clouds, but they don't help for galaxies. The only thing that helps for galaxies is time. And if I was shooting my 20-25 hours of exposures from back and beyond West Virginia, as opposed to Dunn Loring, it would be an entirely different experience. And I would love to do that one day. That is one thing that is in the back of my mind, that one day I will set up an observatory way up in the back of the beyond, as some of the members of the club have, and operate it remotely from my nice warm house here in Virginia. But that is somewhere down the line. But favorite objects are galaxies, and they are all different, But a nice, reasonably bright nearby galaxy is very cool, because you can let your mind say to yourself, there are 100 billion stars in that galaxy, and that X% of them are pretty much like our sun, and of those, X% of those are in the habitable zone and probably are able to have life. And when you multiply those X percentages by 100 billion stars, you come up with the idea of there's chances are really good that somebody has got a telescope down there and is looking back at me. So yeah, galaxies always stretch my mind, and that's why they've always been my favorite subjects.
Well, we're just about out of time, so any closing thoughts? I think
If you were waiting for me, I'm
yes.
sorry. I thought you were thinking, let's see if somebody has a closing question.
No, well, nobody's posted anything. So, do you, Kevin, have any closing thoughts?
Yeah, no. All of my genius went into preparing a slideshow, and preparing a PowerPoint is like, that's the limit of my technical skills outside of astrophotography. So that took everything. But I guess the wisdom that I would part you with is don't get absorbed in the gear before you get absorbed in the night sky. Go out and stand under the sky with binoculars or a cheap telescope, or even with your eyeballs. Go to a nice dark place and spend an hour there, letting your eyes get dark adapted, and just look. That's what I would do.
Well, that is great advice. I hope all of you go out and take a look at the night sky sometime soon and enjoy it. And hopefully this fall you can come visit us at the planetarium as well, where the stars are always visible even when it's cloudy outside. And we will leave you with that. We'll have more programs coming up soon. Thank you so much, Kevin. Hope that you have inspired some people to try some astrophotography. We will talk with you soon.
Thanks for having me. Thanks, everyone. Bye-bye.